Hello, welcome to the video where I'm going to talk to you about accuracy, precision, uncertainty, errors, and just general stuff around measurements. Because when you think about it, right, if you take, let's say if I'm going to take this caliper thingy magic and I were to measure something, like for example, the width of the calculator. Okay, hopefully you know how to use this already. If you don't, why do you watch this video first? Go watch the other one. Alright, so you can read the main and the vernier scale, and then you can come up with whatever reading it is that you have. But my question here is, how certain are you that the reading that you have is the real thickness? Is there such thing as a real, accurate, exact value of the thickness of my calculator? I think we are in the existential realm already. The answer here is not really lah. And you might be wondering, but why? Why? Because we are measuring, right, to determine the actual value of a particular physical quantity. We need to know the truth. But you see, my friends, no measurement is perfect. There's definitely going to be some form of error, and the difference between the real actual value and the value obtained during the measurement is error. Okay? So the thing is, when we measure something, we're just making an estimate. You might be thinking, but miss, I check everything. I'm sure I didn't read wrongly. Yeah. That's great. But maybe, let's say the thickness of the calculator that you have calculated is, I don't know, maybe, where's the calculator? Maybe thick, so I don't know, maybe about 0.86 cm, because it has to be 1 decimal point in meter, right? So then you might be thinking, okay, this is the thickness of my calculator, but 86 what? Is it 861? Is it 862? Is it 859? Is it 858? We don't know. Okay, so the lack of that 1 decimal point causes us to say that when we estimate, an acceptable estimate for us today when it comes to the thickness of our calculator is 2 decimal point in centimeters. But you might be thinking, cannot. Miss, when we buy phone, we want as thin as possible. I want another decimal point. Can. We use a micrometer lor. So when you use a micrometer, you level up the estimate. But again, it is limited. So there's a certain limit to how accurate we can measure. And the difference between the actual value and the real value is called error. Okay, but in CIE syllabus, we prefer to call it uncertainty in measurement. So all measurement definitely have some error or some uncertainty. Okay, and to classify them, there are two main types of errors or uncertainty. One would be systematic and one would be random. So let's look more into these errors. Okay, so when we say systematic, right, you see, for example, you say, oh, my friend is systematically late. So this means that you always expect the person to be late lah. All right, so there's no surprises. So systematic here is cumulative errors that can be corrected if the error is known. And for example, this is normally due to the incorrect position of the 0 point, known as zero error. So if you've watched the micrometer and the vernier caliper video, you would know what zero error is. Basically, zero error means not supposed to have reading, but don't know why got reading. So for example, before you stand on the weighing machine, right, you look at the weighing machine, oh, 2 kg. And then you stand on the weighing machine and it says 65 kg. Are you going to think that you're 65 kg? No, miss, I'm 65 minus 2. Because when I wasn't on the machine, it already have 2 kg, minus. But if it's negative, you add back or not, that one I don't know lah. Alright, so this one is due to the incorrect position of 0. And this is what we call zero error. Alright, sometimes it could also be due to the incorrect calibration of your measuring instrument. Like for some weird reason, right, maybe there's some circuit problem, or maybe the device is hot and then something expand inside and then it affects the scale reading. So later we'll do some objective talking about calibration curve, meaning sometimes things, your instrument doesn't respond the way you want it to lah. But if you know how it will deviate in certain conditions, then you can adjust accordingly. Okay, this is quite relevant when it comes to circuits especially. Okay, so systematic error will always occur if we continue to use the instrument in the same way. You cannot just say, oh, repeat experiment. It doesn't get rid of your systematic error. It's just wrong. You're always wrong. You repeat 10 times also, it's wrong, right? So it's a bit about life, right? If you are wrong and you didn't change anything, you will always be wrong, all right? So systematic error will explain why the reading taken are always larger or smaller than the actual value. So that's actually systematic error. How do you know something is systematic? Because your readings is always either larger or always smaller than the real value. Okay, so that's all. And zero error here comes from measuring instrument not starting from exactly zero. So we can correct or eliminate zero error. Okay, for example, we will minus away the zero error when you measure length, or basically you check first lah before you start the experiment. You close the jaw, you see whether this is zero, you close the micrometer jaw, you see whether this reading here is zero, so on and so forth. Okay, so always check for zero error. But for electrical instrument, right, there's a screw here one. I don't know whether you have done this meter before, but you can adjust and make sure it's zero lah before you start. For example, this is not zero and then this is also not zero, so no good. We need to adjust them. All right, so these are all systematic error. If you know how to anticipate it, then you know how to fix it. Okay, so that is one class of error. Later I will compare them side by side in the notes with you. The second type of error is random error. Okay, so random error, the name also random already, right? So random means all over the place, simply anyhow don't know. So random error can be many reasons. Number one, it can be parallax error, personal reason. So parallax error, right, is actually a type of uncertainty or error where I would say that it can be random or can also be systematic. And what I mean by that is, let's say for example, I want to measure the height of someone shorter than me. All right, so whenever I measure the person's height, my eye line will go down, because what causes parallax error, right, is the viewing angle, your viewing angle with respect to the scale. So a parallax error is an error in reading because the observer eye and the pointer are not in line, okay, to the plane of the scale. So for example, this one. So if you look at this reading, by the way, this one is more relevant in chemistry, this drawing, but I think the same principle applies. So if your reading is supposed to be 15, okay, if you put your eye level to the plane of the meniscus, you will get 15. But if you put your eye too high, then you get 15.2, because your eye is going to think that, oh, this part here, this part, okay, let me show you. When I draw a straight line, you see this part is at the water level, so I would think that, hey, this one is 15.2, not 15.1. And then if I look at, if I go lower, okay, depending on my viewing angle, so where it hits, so you can see they're all looking at the same point on the water surface. But because of the position of the eye, they will have different reading law, guys. Can mo? Okay, so ideally you would want your eye to be in line. But if you're too short or too tall and you cannot adjust the instrument, meaning I need to look at the thermometer that is on the ceiling, I can't get rid of the parallax error unless I get a ladder and climb up the wall. Why though? Why? Okay, so all of this depends lah. Your parallax error can be random because the student chit chat with friend, come back and take the reading from eye level C. Chit chat with this friend, come back and take reading from eye level A. Sit down and scroll Facebook, then come back and take reading from eye level D because the person is sitting down. So all of this is very random lah. So if it's due to human error, then it's random. If it's due to the fact that the instrument is always at a particular position where the perpendicular reading is not possible, then that would be systematic lor. But mostly we classify it as random lah. Alright, so when it comes to this one, there's also other errors that can be random. For example, natural errors in your environment when you conduct the experiment. For example, there's wind, there's temperature, humidity. Maybe you sneeze and then it affects the oscillation of the pendulum. Who knows? Okay, random natural stuff lah. That's why called random ma. But another one, it could be because of the wrong technique of measurement. Okay, so for example, maybe when I turn this micrometer, I turn too tightly, then spoil already. Or I just turn too tightly, then it distorts the instrument. It could be because you use the equipment wrongly. So all of these are what is meant by wrong technique. Now in paper 3, we go very deep into this because in question 2, you are required to identify all the sources of the problems in your experiment and suggest a way to improve. Okay, so for example, random errors can be minimized by repeating the measurement several times and taking average value. Systematic error cannot be minimized by taking average value because you're already wrong ma. You average the wrong thing, you're still wrong. But this one is, oh, my true value is here. Sometimes can be bigger. Sometimes can be smaller, big, small, big, small, big, small, maybe can average out to be the true reading lah. Alright, so that would be the systematic error. And a few ways to overcome parallax error, right, is that generally we put a mirror at the back lah, to make sure that the pointer and the image is overlapping each other. So this one all, I'm just going to leave it here for you to read if you're interested. But I'm going to move on to talk about consistency, accuracy, and sensitivity. Okay, so what we talked about previously was errors or uncertainty, meaning when you measure something, something might go wrong to make your reading not so accurate. I used the word accurate. So what is accurate leh? So accurate is how close a measurement is from the actual value. This is accuracy. The closer it is, the better. Okay? So for example, let's say for example, you imagine a bullseye. Closer to the center, that would be more accurate. Okay? So accurate instrument will give readings that is close to or almost equal to the actual value of a quantity. Okay? And an instrument with 100% accuracy does not exist. Okay? And error, as mentioned previously, is the difference between what you measure and the actual value. So if the error is very small, it means that you have high accuracy. Well done. Good job. So for example, right, if I want to measure the thickness of my phone, I have a few choices. I could use a ruler. So then this one, I will have 1 decimal point in cm. Can use a vernier caliper, 2 decimal point in cm. Can use this 3 decimal point in cm. Now whichever I choose, okay, if assuming my technique is correct, okay, meaning I know how to read it, I didn't like go and do something weird, then this will be the more accurate reading. But if let's say I didn't watch the video on how to use these two things, but I know how to use a ruler lah, so my reading is more accurate using a ruler. Okay, understand? So they are not the same idea because error here depends on the type of instrument, but also depends on how you take the reading. Okay, so measured value, very small error has high accuracy. So how do you improve your accuracy? If it's a matter of random errors that you cannot control, like for example, period of oscillation, okay, then what you can do is you can repeat reading and take average. Alright, period of oscillation, or for example, if you do a circuit experiment and then the reading keeps going up, going down, going up, going down because your connection is not tight. Okay, so avoid parallax error, avoid zero errors. So you try what you can do lah. For example, you read this law, check for zero error. Okay, and then we use instrument that is better. For example, a vernier caliper is better than a meter rule. All right, depending fit for purpose lah. All right, so that would be accuracy. All right, now what about consistency? Now consistency here is also related to the ability to register the same reading when the measurement is repeated. So for example, if a reading is consistent means when I repeat the experiment, I roughly get the same reading. Whether the reading is correct or not is a totally different idea. Okay, so if the reading is true, then it's accurate. If I repeat the reading many times and I get back the same true reading, then it's consistent and accurate. Okay, so a consistent reading can be inaccurate. So if you look at this bullseye here, this one, this one is consistent. This 4 points here, consistent, not accurate. Not accurate because you're supposed to hit in the center. What happened? Okay, if you want consistent and accurate, then all the reading must be very near, like that lor. So this green one, this one here, is consistent and accurate. This is the best one. Okay, and this one is inconsistent lah. You can see sometimes very far away, sometimes very close. Inconsistent. Is it accurate? Depends lor. If you average these 4 points, somehow give you close to X, then it's actually accurate. It can be accurate and inconsistent also can. An example of accurate and inconsistent would be like this lah. You look at my green dot, like that, like that, like that, like that. They average out to the center, right? So this is accurate. Although I do want to put an inverted comma. It's only accurate after you take average lah. And inconsistent. Okay? Whereas this one, I don't know, I need to calculate. Looks fairly still looks fairly accurate to me, this room. Alright, so if the scatter is very far away, then it is not consistent. Okay? So a set of measurement is consistent is if all values are close to the mean value. High consistency means small deviation or small changes from the average value. Okay, so this is what it means by deviation, the difference between the measured value and the average value. All right, so right now, if you want to decrease or improve your reading, we again parallax error law, but also at the same time, we can exercise greater care. You take the reading, you don't just do the experiment properly basically, and use the instrument which is not defective. So repeat reading doesn't change your inconsistent reading. If you somehow connect the circuit wrongly or understand the experiment wrongly and you measure the wrong thing, or you conduct the experiment wrongly and then measure the right thing, whichever it is, if it's your fault, then it is a consistent error. But you don't know what the error is unless you reflect upon it. Okay, so that is consistency. All right, the next one would be sensitivity, or in A-level syllabus, sometimes they also like to use the word precision, precise, precision. Okay, if a reading is precise or not. Alright, so the sensitivity of an instrument is the ability to respond quickly to a small change in value. Okay, so a measuring instrument has a scale with smaller division is more sensitive. For example, ruler A is more sensitive than ruler B. Micrometer is more sensitive than a vernier caliper. Okay, and also besides the size of the division, the design of the instrument has an effect on the sensitivity. So for example, a thermometer has a high sensitivity if it can respond faster. Okay, so that's all about sensitivity and precision. The ability to read readings, to respond quickly to a small change, and measure readings to a higher number of decimal points. Alright, so that's it regarding accuracy, sensitivity, and precision. And I will see you in the next video. But before I go, I will compare them. Or actually, I recommend that you do the comparing because then you can use it to reflect on the lecture. I'll compare them in these notes. Alright, so I'll see you there. Bye bye.